Hello, everyone. We're working on Chapter 11, Linear Regression, from An Introduction to Statistical Methods and Data Analysis by Ott and Longnecker. All right, so one thing to note is that we can look at our data by looking at scatter plots that show a relationship or an association between two quantitative variables. Note for our work, we're looking at linear relationships, so we're not modeling things that are not linear. So our explanatory variable is what we would traditionally call, our X variable, or really our independent variable. And the response variable is our Y variable, which is our dependent variable. All right, so in this example, we have car weight and gas mileage. We can see as the weight of the car increases, the gas mileage gets worse and worse on average. So in this case, the explanatory variable would be the weight of the car. And the response variable is the mileage. So in general, we say that the weight of the car can predict the mileage we're going to get. So one good thing to practice is if we look at pairs of variables, we can identify the explanatory and response variables. We could also predict the direction of the association. So one thing to think about is which one comes first. So high school GPA and college GPA. So we think that high school GPA could predict college GPA. And in general, I would think that would be a positive association. So as high school GPA increases, college GPA most likely increases. The next example, fire damage in dollars and miles to the fire department. So I would think that the miles to the fire department is going to predict the fire damage measured in dollars. And in general, if you live further away from the fire department, most likely your fire damage is going to increase. All right. Years of school. And income. Hopefully we see as years of school increases, income increases. And grade on a final exam, grade on a midterm exam. So I would think that the midterm scores are going to predict the final exam scores. And once again, we hope that that's a positive relationship. So all of these examples were positive relationships, but there's plenty that could be a negative relationship as well. All right, so in statistics, we have a slope-intercept form of a line where y equals beta 0 plus beta 1x. Beta 0 is the intercept and beta 1 is the associated slope. So back in the day, you probably did something like y equals mx plus b. Right, this in your algebra courses. Okay, but now for statistics, we're just switching up the notation slightly by saying y equals beta 0 plus beta 1x. Now, if we associate what we see in our statistics class to what we used to see in algebra class, we notice that the piece that multiplies the x, that piece is the slope. Right? And the piece that's by itself, that is our y-intercept. All right, the interpretations are to your left. So in general, we can talk about whether or not beta 1 is positive or negative. That's going to mean that if we have a positive slope, as x increases, right? Y also increases. But if we have a negative slope, as X increases, Y decreases. Now we say on average because it doesn't mean that for every data point this is absolutely going to happen, but in general this tends to happen. All right, so if we have Y equals 1 plus 2X, right? In this case, beta 1 is equal to 2 and beta 0 is equal to 1. So for a slope of 2, right, as X increases by 1 unit, in this case, we don't know what the values of X and Y are, but in general, you're going to change the context of the unit. As X increases by 1 unit, Y increases by 2 units on average. Okay. And then for the y-intercept of 0, when X equals 0, Y is equal to 1. All right. So in general, we don't think that all the points are going to lie exactly on a line. So we're going to put in an error term, okay? Introduce an error term. So now we have this epsilon, which is all the random errors. So we don't think that we perfectly fit our data, right? We're gonna have a scatter plot. The data points are not going to be exactly on a line, right? And then here, the distance from any point on the line to the corresponding data point, that's going to be the error, right? So we have our observed data point, xi, yi, but then on the line, that's going to correspond to xi, y hat I. All right. So we are going to take data from individuals, and for each person, we're going to have the pair xi, yi. Okay, we're going to find the line relating y to x, and we're going to estimate our parameters. So we're going to estimate the intercept and the slope. And those hats just designate that we are looking at estimates. So y hat is our prediction. Beta 0 hat is the estimated y-intercept, and beta 1 hat is the estimated slope. Once we put those hats on, there's no longer an epsilon. And this becomes our prediction line. Okay. This is just simple linear regression right now, so we're just looking at one value of X relating to Y. In future chapters, we'll have lots of X's with a single Y. Okay, so our least squares regression line describes how our response variable changes as the explanatory variable X changes. Right? We're going to get a predicted response y hat from a particular explanatory variable X. It's the best fitting line to the data, but how is that found? Okay, so essentially we have a bunch of data points, right? And they look like they follow a linear pattern. And then we fit the best fitting line. But how do we know that that is the particular best fitting line versus a different line, right? That's pretty obvious that my second line that I drew doesn't look great, or my third line. How do we choose the overall line that we're looking at? Well, what we do is for any particular line that we fit, we look at our xi, yi, and we compare it to the corresponding prediction, xi, yi hat, right? And what we're going to do is we're going to take the difference between the observed yi and the yi hats, right? We call this the error, right? And what we're going to do is we're going to minimize the vertical distances or minimize the squared errors. All right, so our sum of squared errors, SSE, is the summation for each of your observations, I equals 1 to n, of the yi minus yi hats, okay? So what we could do is we can substitute in the beta 0 hat plus beta 1 hat xi for each person, and then we can minimize this. Okay, if you're familiar with calculus, this is a minimization problem, and you can essentially take derivatives, set it equal to 0, solve for your parameters, and that's going to give us the values. All right, but overall, the thing to take away is that beta 0 hat and beta 1 hat are essentially the values that make this SSE the smallest possible. We call these the least squares estimates of beta 0 and beta 1. So you could write beta 0 hat is the least squares estimate for beta 0. Similarly, beta 1 hat is the least squares estimate for beta 1. So overall, beta 0 hat estimates beta 0 and beta 1 hat estimates beta 1. So beta 0 and beta 1 are parameters because those come from the population and they're unknown. We don't know what they are. We'd like to know what they are. So we take a sample of data and we calculate statistics from that data set. And those statistics estimate the population parameters, right? Sample statistics estimate population parameters. Overall, this right here is the crux of all statistics problems, right? We have a population, we want to know about some parameter from that population, we take a sample of data, we calculate the statistics, and then we turn around and say, those statistics estimate the parameters. This is the first principle in statistics. It's something you want to carry with you to any statistics course you take. Sample statistics estimate population parameters. If I want to know about a parameter, I can take a sample of data, I can calculate a statistic, and that statistic will estimate the parameter. All right, so these are really important formulas from this chapter. All right, my suggestion to you is to learn what each of these are, what they stand for, and how to calculate them. So the slope, as we said before, the estimated slope is beta 1 hat. The y-intercept, beta 0 hat. How do we find them? The formulas are there. The sum of the x deviations squared. When you want to look at the sum of the x deviations squared, that's just our xi minus x bar. Deviation means subtraction. And since we said x deviations, that's every observed xi value. That means every single person in your data set, what was their observed explanatory variable? And then x bar is just the mean of all those x values. Okay, for sum of y deviations squared, right? SYY. That's the yi minus y bar. So y deviations, we're taking the observed yi and we're subtracting y bar. and then we're going to square them. So they're sum of y deviations squared. Okay, the sum of the x deviations times the y deviations. Okay, so we get our xi minus x bar, then we have our yi minus our y bar. All right, sum of squared errors. Errors, remember, are from the observed value to the predicted value. So those are our yi's minus our y hat i's squared, sum them up. That gives us our sum of squared errors. Sample mean, right? You sum up all your x values, divide by the number of people in your sample. Your sample mean for y is sum up all the y values and then divide by your total sample size. So hopefully some of these look familiar. If they do not, review them, memorize them, get to know them. It's going to make chapter 11 much, much, much easier. Even though these seem complicated, the nice thing is that you can just plug this in R or on your calculator or in any other programming language you like. But I'm going to encourage you guys to use a programming language because it's really just a giant calculator and it can make things much, much, much faster. Okay, so in the next video, we're going to be doing some proofs and I will see you then.